record. All right. So I had a couple of requests, which I always appreciate. These are from assignment 2, which is due on Sunday, I think, right? So, I think, yeah? Or
for this Sunday,
yeah. Okay.
And then do you have a question 12 now?
Yeah, they're just piled down here. Okay. Yeah. But I'll start from the top, work my way down. Okay. I have to get back in the groove. Combinatorics, counting, permutations. Whenever I have a question like this, I usually start by making my slots, right, to see if I can solve it that way. Okay, and so what would that look like for question 2? You're making an ice cream cone and you have 19 flavors to choose from. Yeah. How many different ice cream cones can you make with 3 scoops? So that's important. If you're not allowed to repeat a flavor. Let me just go close this door. That one's fine. So with the hint of using the slots, right, my go-to move is, well, scoop number 1, scoop number 2, and scoop number 3. Scoop 1, scoop 2, and scoop 3. The first scoop, I have how many flavors to choose from? I have 19. Scoop 2, I'm not allowed to repeat a flavor, right? So how many choices do I have? Well, I've already used 1. I don't care which one. Now I have 18, right? So, and 18, and whenever we're doing these slots, you're multiplying through, right? And so multiplying here. So now I've got the first 2 scoops. I don't care what flavors, but now I only have 17 flavors left. And 19 times 18 times 17 puts me at 5,814 different ice cream cones. Wow. The choices are endless. And pretty sure that's the answer. I did check it. 5, 8, 1, 4. Sometimes I just want that green feeling, you know? It's addicting. I get to go in and just have green all over. No, when I get a red, it's like, uh-oh, that's bad. Usually I figure out I do a little something weird. That can happen. Can't win them all. Oh, I just jumped right in. So I did the survey. Sorry, that was a terrible poll that I did. That's what I get for throwing it together before class. I should have taken my time and put together something a little bit more reasonable. But because the responses were just kind of spread evenly, giving me no information at all. So I said, well, all right, then I'll just do whatever I want to do, which is I'm going to my parents next weekend. So I'll post a pre-recorded lecture and we're not going to meet in person or anything. But so you can watch that lecture at 4 next Friday if you want, or at some other time. How about that? Yeah, that was shame on me. And I'm in stats. And do you know what I tell all my students? If you're ever making a survey make sure that you hire someone who knows what they're doing, because it's really hard. I just bungle it, completely mess it up. Anyways, it's hard. There. I didn't write anything down about that, but I did write it on Moodle, so got it there. The next request was question 9. In how many ways can 7 students, so these obviously have different values for everyone, so you'll need to map it back to your values, but I think they can handle it. In how many ways can 7 students be seated in a row of 7 chairs if Jack insists on sitting in the first chair? Okay, so what I'm gonna do, again, my go-to move is, oh, I guess, what could I have done? Will it work? 19, choose 3. No, it doesn't. 19P3. Okay. Sorry. Going back to this other one. I don't even think to use it. That's why I didn't think to use it. Or because we can't repeat the flavors, it's a permutation. So it would be 19 permuted in groups of 3. How many of those groups can I have? But you get the same answer. I like to just do my slots because they're more flexible, as we'll see here. Yeah. So going back to the chairs, I've got 7 students in a row of 7 chairs. So everyone's going to sit in a chair. And the only condition is that Jack has to be in the first chair. So 1, 2, 3, 4, 5, 6, 7 chairs. Chair 1, 2, 3, 4, 5, 6, 7. You don't have to put the labels underneath if it's obvious to you. This is just to help you solve it, right? And so, but I find it helpful. All right. How many of these 7 students do I have to choose from if it has to be Jack? Well, I only have 1, right? And so here, I only have 1 because this student must be Jack. The pickle is Jack is one of those 7, right? So moving on to the next chair, I don't have 7 again. I have 6 students to choose from, right? Because I had to take Jack out of the group. So now I have 6 students to choose from. Once that student, I don't care which one, once that student is seated, they're out, right? I have how many? I have 5 to choose from. And then same deal, 5, 4, 3, 2, 1. If you don't want to multiply these out, what is this? This is really 6. No, 6 factorial, right? Which there's a button for on your calculator. So if you don't want to do 6 times 4 times 3 times 2 times 1, then you could use 6 factorial. 6 factorial on my calculator. 6, I can never see the factorial. There it is. I get 720. 720 times 1, right, is 720. I guess I should check it. Feeling pretty confident though. But it's when I say stuff like that that it really backfires. Okay. Whew. Got it. So the key there is going to be first that Jack has to be the first one, giving you only 1 option, but then also remembering that you've now taken out a student, right? the rest is kind of on rails, I think. Nice. 12's a bit of a pickle. We did one similar to this in class, right? But it's quite long, right? Use the binomial theorem to identify the coefficient of x squared in the expansion of 4x plus 1 to the power of 5. And I think the one you sent me had subtraction. What if I try, I'm gonna get, I wonder if I can try a different version. I want there to be subtraction.
If you get it wrong, I'll probably change the question.
Well, I want it to be, because the one that you had messaged about was harder than this one, because it's got subtraction in here, which you have to keep track of.
Yeah.
So I'm just gonna go into the actual mom and grab it. From here. It remembers me, but how can I? 3 tries. Can get a similar question. Okay. This is gonna get weird. Okay. There's one. It's that underbelly that you don't need to be concerned with. All I wanted was something like a moment like this. Some people wait a lifetime. What was I going for? I was going for a subtraction in here. All right. Because, all right, okay. If I go back to the textbook, because I'm gonna need it. I'm going to need it. Maybe here. Where did we get it from? I have to go back and remember this stuff. Thanks. 2.4, I think. 2.3, 2.4. Good. Binomial coefficient. Binomial theorem, we're getting close. Oh. We're going to be relying on this, right? Mapping this 3x minus 2 to the power of 8 to this formula, right? We need to pay attention to the addition in here, which means that the first thing I need to do is rewrite this as addition. So I get 3x plus -2. Subtraction is just a special case of addition, right? Okay. So now, identifying all the components from this theorem that we're applying to this problem is going to be the key, right? And so, okay, here we go. I'm going to copy this down so it's on the same page when it prints out. But it's the exact same. Oh. Let's highlight. So instead of x, I have 3x. Instead of y, I have y is equal to -2. And instead of just n equals 8 in this case. Now I have all the components that I need to make the sum. Okay. Mapping these 3x and -2s and n equals 8, and I'm summing from k equals 0 up to 8, right? At 8, choose k, which is going to change at each step, right? And then I have x to the n minus k, and then y to the k. Okay. So I'm going to start writing out those. First, I'll start out by writing the general summation with the n's and the x's and the y's replaced with my values. So from k equals 0 to 8 is the sum. And I'm going 8, choose k, because k is going through and iterating through the sum. So I'm leaving k as k. And instead of x, I have 3x to the power of 8 minus k. Times y, which is -2 to the power of k. Okay. We could, if you wanted to, I'll do the full thing. But if you want to get a little cheeky, what could you do? You could say, well, if I want just the coefficient of x squared, what could I do? I could figure out what k would have to be to make x this value to the power of 2, right? K would have to be 6. Are we going to be cheeky or do the full thing? Full thing's pretty long. It's good for practice. We'll do the full thing, right? But here, I'll make a note right away, maybe in purple or something. And I want to include the x. So notice for x squared, k must be 6. We're going to see that. Am I biting off more than I want to chew? Yes. Chew it anyways. All right. Let's start our iteration. So we start at k equals 0. 8, choose 0. There's only one way of choosing 0 things. But that's okay. We'll use our calculator. And then times 3x to the power of 8 minus 0 times -2 to the power of 0. That's going to simplify, but I'll just make a note here that this is when k is equal to 0. And I'll do one for each line just to try to keep it nice and neat, or neater. Now I have to do k equals 1, right? So that's the first one. Now we've got 8, choose 1 times 3x to the power of 8 minus 1, -2 to the power of 1. That's for k equals 1. Plus k equals 2, same deal. I told you I didn't want to do it. It's too boring. 8 minus 2, -2 to the 2. And that's when k equals 2. Oops. Kind of speeding up the process here. I'm gonna do k equals 3, 8 choose 3, 3x to the 8 minus 3, negative 2 squared, that's when k is 3, plus 8 choose 4, 3x to the, oh yeah, remember, I think in class I forgot the negative at one point, making a huge mess. But I don't think I've done that again. I think I'm doing pretty good. Pat myself on the back. 8 minus 4, negative 2. Well, okay, there I did it. To the power of 3 on the previous, 4 on this next one. Always something. 8 choose 4, 3x, 8 to the, wow. Can't trust me with anything. 8 choose 5. I've moved on. 8 minus 5, negative 2 to the 5. K equals 5. 8 choose 6. We already decided that this is the one to pay attention to, right? But if I had been simplifying, which I could have been doing, right, to see what the power of x is, oh no, here it's 8, here it's 7, 6, 5, 4, I'm getting closer, 3, 2, right? I could have been keeping track that way, and I probably should have. But I also wanted to show as much math as possible. 8 choose 6 is 3x to the power of 8 minus 6, negative 2 to the power of 6. K equals 6. And I'll make a highlight here that that's the one that we're going to come back to. But for completeness, I have to finish. I can't just stop here. It's crazy. 8 choose 7, 3x to the power of 8 minus 7, negative 2 to the 7. That's k equals 7. And then finally, 8 choose 8, 3x to the 8 minus 8, negative 2 to the power of 8. Woo! But it's really important to notice that you didn't have to do all this. It's good practice, but don't have to, right? If you know the trick of boiling it down, right, and saying, okay, if I want x to be 2, right, and n is 8, then k must be 6, and then working it backwards, right? So now, what's the coefficient of this thing? So the only variable left, so if we're going to focus here, which is exactly what we're going to do, we want to find the coefficient, and maybe I'll use a different color here and rewrite it. 8 choose 6 times 3x to the power of 2 times negative 2 to the power of 6. I'll put the equal sign underneath. Try not to use too much space. First of all, 8 choose 6 on your calculator. I guess I could use the one that you can see. That might be nice. The choose function is in the functions, choose, and I want 8 choose 6. There are 28 ways to choose 6 from 8. So 8 choose 6 is 28. Remembering when you bring this square inside the brackets, because we're trying to simplify, right? Then I have to put it on the 3 as well as the x. And so here this becomes 3 squared times x squared. And negative 2 to the power of 6. Keep grabbing my trusty calculator instead of this one. -2 to the power of 6 is 64. Kind of simplifying what without going too crazy here. So what do I have? I have 28 times 9 times 64 is the coefficient. All right, and so here, this is 28 times 9 times 64 times x squared. And let's see here. 28 times 9 times 64 is 16,128. Therefore, the coefficient is 16,000. I'll write it without the comma, 128. I really, really, really hope that I'm going to get this right. Yeah. Yeah. It's just at 8, you'd have to, unless you have like the 5th row memorized or something, it's quite tedious. So I would probably just use the choose function instead, because that's what the choose function is, right? Or it's just a way of representing how the choose function works. But absolutely you can. I just don't have it memorized. If you have like line 5 memorized, then knowing the pattern that it adds up the previous ones is going to be helpful, right? Then you can build up to line 8. But I'm not there. I don't have it memorized. All right, let's see. Moment of truth. Hopefully it didn't change the value on me. Let's see here. 1, 6, was it 125? Or what was it? 128, thank you. Phew, a tiny green check mark, but still. Yeah. Let's see. I'm gonna go to, I guess I can go here, question 7. Oh. But this one is done, so that feels good. Give myself a great job. Let's do that one. Oh, last image, yeah. Okay, so this one wasn't doing it, huh? Let's see here. A person's going to a party, was asked to bring 3 different bags of chips. Going to the store, she finds 15 varieties. How many different selections can she make? Aha. So, and it wasn't working, huh? It's subtle, but it does say it has to be different bags of chips. So for that reason, I'm gonna go bag number 1, bag number 2, bag number 3, and see what happens. First, I have 15 to choose from. Then I have 14. Then I have 13. And let's see here. 15 times 14 times 13. 2,730. Let me see if it's not taking it. Doesn't like it. Permutations, maybe.
How come question number 7 they're using combination, but in question number 2 they're using permutation? The questions look similar.
Yeah, it's just that. Why isn't my answer 13 different bags? I think you're right. 15 P3. No, that's what I did. 15 choose 3 is the answer, but I would argue that's not the answer. I get, maybe I'm reading into the different bags of chips, but that's not something that you can know, right? That they have to be different, but maybe it's just 3 bags of chips. So, okay, I'm gonna make a note and look into that one. And that was, which one? Question 7? I would want it to be this answer though. So if you got, some version of this where you did the slots, because I'm hanging my hat on them being different, right? Which are permutations, but they just, their answer would say 3 bags of chips. So there's a mismatch there. Sorry about that. Question 7. I'm gonna say fix me to myself or something. But because it says different, the answer should be where they're different, right? Sold? Maybe? Sort of.
What question is that?
7. I think there's going to be different numbers of varieties. That's probably randomized. But I think this answer is wanting to see 455, which would be the number of combinations, which I guess makes sense because the order doesn't matter. But for 3 bags of chips with 15 varieties, or some other numbers probably.
If you go on the video, I think like they explain it differently. So if you watch that, like they probably have a different way.
I've never watched any of these videos.
Yeah.
Let's see here. Okay. It's exactly this question. Finds 12 varieties. How many different, well, now I'm curious.
A person
long
going
is
to a
this thing?
party was asked to bring
Blah,
3
blah,
different
blah, blah,
bags
blah.
of chips. Going to the store, she finds 12
It's
varieties.
not helpful because the
How many
sound's
different
only on my end.
selections can she make?
But
So
before I fix the question, I'll watch that video and I'll see if maybe I'm just reading it wrong, which absolutely happens. Let's see here. It's gonna be the same. Oops. right off the bat, I would say 12, choose 3, which is the answer. But the only reason that I'm gravitating towards the choose function is because how many ways can 3 pizza toppings be chosen from 12 available toppings? Let me think.
It's 12 times 12 times 12.
Yeah. I guess my answer is, I don't know right now. And instead of everyone watching me try to figure it out, I think, I'll have to think on it so I can kind of give you a better answer.
You have to do the factorial thing where it's like, you have to times it, right? And then like
And then divide by however many.
whatever factorial you have inside the other one, it's canceled out. Then we divide it, it's a smaller number. So it's similar to like the whole chips question. Like, that's
yeah.
Like
okay. Because I think the choose function is a permutation, and then you divide it by. Well, and see, this is where I don't want to lead you down this rabbit hole that I'm going to go on. Yeah, there's a link between the permutations and the choose functions, and it's not off the top of my head. I don't have it. But I'll look into it. How about that? How's that? I'll change this. Fix me, maybe. I'll have to watch the video and see how they interpret this different.
and R.
Yeah, okay. Sad face. But I'll just go back and look at my great job. Yeah. All right. We put off logic long enough. How about those pickles, huh? When I was going through and making those solutions, I had to really, really kind of calm myself down and just go super slow and just pick apart all the pieces. I'm like, Emily, you know this. It's scary. I don't like it. I really don't like it. All right. Were there any in particular that gave you trouble? Maybe. I have a few in mind, but maybe not. No. I think what if I go back to the solutions? I know you have these already. For parts of these, you can't see kind of my thought process when I was writing it out. I tried to make it clear what the procedure was. But in question 1, we're given 3 statements, which we're going to use abbreviations for. So D is I like discrete structures. C is I will pass this course, and S is I will do my assignments. And we're asked to express each of these propositions in symbolic form. Yeah. started off nice and slow. I like discrete structures and I will pass this course. So what I did, well, I like that I can just copy and paste it and I don't have to write it out a billion times. But I picked out the propositions, right, or the variables. So I like discrete structures. I can replace with a D. And then I don't have anything for the end. Well, I do, but I'm going to bring it in later. And then I also picked out the I will pass this course, which we decided to replace with a C. So far, I'm just mapping these to these statements, right? And then I remembered that and symbolically is the, oh, I can never remember the conjunction or the disjunction. Can't remember. I know you have it. What is it? Conjunction. Woo. Oh. Which means that the statement is D and C. Yeah. So doing that same thing again, I will do my assignments, looks exactly like S, so I didn't have to do anything and no thinking required. But then, or I will not pass this course, which is the negation of C, right? And so, and then or, the disjunction is the V, right? So S or not C. Here's where it got a little messy. It is not true that I like both, that I both like discrete structures and will do my assignments. So all of that is not true, right? Everything that's followed is not true, which we have to negate, right? So what I did was I kind of put it off to the side for a little bit. And I said, okay, in the end, I'm going to have to negate everything. Okay. And then I just focused on, I like both discrete structures and will do my assignments, which is just D and S. But then I had to negate it all. So I put brackets around it, right? Remember, brackets are really important because if you don't have the brackets here, then the negation is only on the D, right? But you want it on both of them. Okay. So here, I will not do my assignment. So that's the negation of S. And I will not pass this course. So both of them are negated, but separately. And so we show that by giving them both a little negation. Okay. So that was a good warm up. Then we moved on to, okay, now I have these kind of mathy statements. Okay. Let P be this statement that 2 is less than or equal to 5, and Q be that 8 is an even integer, and R is 11 is a prime number. Okay. Now what we're going to do is we're going to take those statements and given some logical statement, I have to write it out in words. Okay, so just go moving backwards, I guess. Starting off with not P and Q. So what I did was I had little grabbable sentences, right? Those statements. And what I want to do is just take each P. So where I see a P, I'm going to write 2 is less than or equal to 5. Okay? And then remember to negate it. Negating 2 is less than or equal to 5 is the same as saying 2 is greater than 5, right? That's the opposite of it. And Q, which is 8, is an even integer. And I think we were also asked to determine whether the statement is true or false, right? The first few are relatively obvious. When we hear the statement, you would say, well, that's true or that's false, right? I think it's the last few that aren't as obvious. So 2 is greater than 5. Well, that's false. So the whole thing is false.
I was gonna say for the first part was written that's 5 is greater or equal to 2. With the negative part, why is it 2 greater than 5 would be equal to?
No, because it has to be the opposite. So you switch the inequality to negate it.
Oh, okay.
And because the equal to 5 is included in the first statement, it's not allowed to be in the second statement.
Oh, okay.
So it's like a full switch.
Yeah.
Nice. So here we see that if one part of the statement, if I'm joining them with and, is false, then the whole thing is false. Which we saw with the truth tables, right? In order to be true, both of them have to be true if it's an and statement. The conditional, you read it as if P then Q, right? And there were a list of similar ways that we could say this conditional statement. There's a huge list. And so you could have used something a little bit more elaborate than if then, but I like to just think of it as if then, especially when we're just starting. So if 2 is less than or equal to 5, then Q is, or 8 is an even integer. What was the thing about the truth statement? As long as the second part is true, then the whole thing is true, right? That was the weird part about conditional statements. So something false can happen here, but in the conditional statement, it doesn't matter. It's the final result. So the only time that a conditional statement is false is if the end part is false. But in this case, 8 is an even integer, so it's true. Doing the same thing, P and Q, but the whole P and Q is one thing. So if P and Q, then R. So if 2 is less than or equal to 5 and 8 is an even integer, right? That's true. Then 11 is a prime number, which is true because 11 is a prime number. Have you guys talked about prime numbers divisible by only 1 in itself? Maybe? Well, it's a prime number. It's just a quick Google away. It's a prime number. Okay. These are getting bigger. If P, then Q or not R. But if you just replace the variables with the statements, you don't have to make fancy sentences. In fact, I would say don't make fancy statements or fancy sentences, because often what you'll do is you'll unravel the meaning and you want to say what you want to say and you don't want to change the meaning, right? And so this one's fine. If 2 is less than or equal to 5, then either 8 is an even integer or 11 is not a prime number. So here, when we had this bracket here, right, I had 2 options, this Q or not R. And so usually how we say that is either this or this, right? Either or. That either kind of serves as a bracket in a way in our sentence structure, right? Kind of wrapping it up and saying, then one of these 2 things. So if 2 is less than or equal to 5, then either 8 is an even integer or 11 is not a prime number, but since 8 is an even integer, then it's true, right? Something true or something false makes an overall true statements, right? And that's how the or works. Only one of them has to be true for the overall statement to be true. Okay, and if the final part of the conditional is true, then the whole thing is true. All right. They just don't stop. If P, then not Q or not R, right? But it's all of that is part of the then part of the statement. And so again, with the or, I'm gonna say either or. What if I had and in here, which I'm sure we have later, but let's just talk about it, right? Then I would say something like if P, then this, then both this and this, right? Just to emphasize that they come as a lump, as a package, right? So either or both this and that. So if P, then, and then here I just wrote the bracket just to kind of emphasize to myself that I need to communicate that these things go together. Then 8 is not an even integer because it was negated. Now, here's where, I mean, you can get fancy and you can say, well, if 8 is not an even integer, then it must be an odd integer. I don't want you to have to think that much, right? So you can write an odd if you want, but I just usually throw in a not, call it a day. Right? Or 11 is not a prime number. Now, the statement 8 is not an even integer is false because it is even, right? Or 11 is not a prime number is also false. So now this whole thing is false. And that's the only time that the conditional overall is false, right? Is if I end up at a false result. So that's why it's false there. Okay. If not Q, then not P. So if 8 is not an even integer, then 2 is greater than 5. If 8, don't overthink it, Emily. Oh, it's like, why is it true? Why is it true? I'm racking my brain. Because a false statement, so a false to a false is true. Because if 8 is not an even integer, well, that's not satisfied. Then 2 is greater than 5. Well, that's false. So a false, so here, a false to a false is true. That's the sneaky part about the conditionals, right? The only time that it's going to be false is if you're going from a true to a false. That's not obvious, right? It's just something that I had to memorize. I don't know about you. Maybe you just get it. I don't do, but it took time. Right, and so here, that's why, so if, so the first part is false, then the second part can be false or true, it doesn't matter, it's going to be a true statement. Okay. So this one was referring back to these statements I get it. They didn't want to make multiple statements. That's totally fine. It takes a lot of work. So what we want to do is we want to write the converse of these propositions that were given here. Okay. So these are all conditional statements. And initially I'm kind of making you do question 4 in order to do question 5, right? Because first you have to write the conditional statement in order to flip it for the converse, right? And I even said, okay, write the converse of the propositions. I brought in the definition of the converse just in case it's helpful, right? A little reminder. So the converse is of P. So if P then Q, the converse is if Q then P. If you have these variables kind of chunked out in your sentence, then you just do a little switcheroo, and then you're done, right? I shouldn't say just, that's rude. The first statement is, if an integer is a multiple of 4, then it is even. So takes a little bit of practice, right? Boiling down what parts of the statements I want. But both of these are talking about an integer, so I'm going to leave that alone, right? And so now I'm going to talk about if it's a multiple of 4 and whether it's even, right? So if it's a multiple of 4, then it is even. The converse here, right? So I'm letting this statement be P and this be Q, right? Just to match the definition that I brought in. That's the easiest way to do it. Now I want the converse, which takes Q. So if Q, then P. Now I have to bring it back to words, right? So if an integer is even, then it is a multiple of 4. Would be the converse. So we need to decide if that's true or false. This is going to be false, and I think the easiest way to kind of think about it is think if you can find any contradictions, right? So anytime when that statement is not true, right? Generally, if an integer is even, then it is a multiple of 4, right? A lot of the time. But if you think about 2 is an even integer, right? But it's not a multiple of 4, right? So because I was able to find one place where it wasn't true, then the whole thing is false, right? It's not a true statement all the time. So again, a little bit of practice, just kind of reading these and figuring out what part is that variable that you're going to be switching around. Okay. So the fact that a polygon, and both of these statements are about the polygon, and so I excluded it. The fact that a polygon is a square is a sufficient condition that it is a rectangle. Okay. And I'm referring to a list from the end of 3.1. Okay, where we have all the following are equivalent to if P then Q. So P implies Q, Q follows from P. Notice the switched order here. P only if Q, Q if P, that's changing things up. P is sufficient for Q, Q is necessary for P. Notice the change in order again, right? And so recognizing that all of these are just if P then Q, that's going to be important. Taking us back to, is a sufficient condition that it is a rectangle? I made this P and this Q. So if P then Q, the converse is if Q then P. So if a polygon is a rectangle, then it is a square. Because I brought it back to the if then because I prefer it. It's just cleaner, nicer to read too. Why is that false? Well, a square is a special case of the rectangle, right? But a rectangle is not necessarily a square, right? That's why we have a different term. It can be elongated, right? And so if a polygon is a rectangle, then it is a square. That's not necessarily true, right? And so the statement is false, right? It can be a rectangle without being a square. If x is equal to 5, then x squared is equal to 25. Fair enough, right? And here we've got this nice kind of condensed writing again. So now I want to switch the order. If x squared is equal to 25, then x is equal to 5. Okay? So, and that's exactly what it ends up being, which is false. Why? If I let x be -5, then I'm going to get x squared is also 25. So knowing that x squared is 25 doesn't force x to be 5. Right?
Wait, why is it negative? X equals -5.
Oh, just as an example.
Oh,
A way that I could get, well, the other way or another way I could get x squared equal to 25 is if x was -5.
okay.
So knowing that x squared is equal to 25 doesn't tell me that x must be 5 because it could be -5. And that's why it's false. We do a lot of these proof by contradictions, right? I found a case where that's not true, so it's false. Nice. If x squared minus 5x plus 6 is equal to 0, then x equals 2 or x equals 3. I'm treating the x equals 2 or x equals 3 as one thing. You could break it up, but I don't want to, right? I could say q or r in brackets, but then I treat it as one thing anyways, right? And so I'm just going to leave it as one thing. And so if x equals 2 or x equals 3, then x squared minus 5x plus 6 equals 0. Hey, I wanted to use green for true. I'll change it. It won't change, obviously. That's the first thing that's true. Right. Looks like it's moving around there. Or maybe I'm just loopy. See stuff. Okay. Not much to say about if it's true. The tricky part is knowing that you haven't forgotten anything. But if you factor this out, right, you see that the only two factors would be x equals 2 and x equals 3. And that's just the end of it. Okay. This is one of those sneaky ones, and I snagged it from the textbook that I was referring to in the solutions. So we have x squared equal to y squared is a necessary condition for x equals y. Okay. So now the first part, because all of the following are equivalent to if p then q, which is the structure that I want, right? Is equivalent to q is necessary for p, making this my q and this my p, but it's equivalent to if p then q. This is a sneaky one, right? It's worth revisiting later on your own if you haven't done it already. But once I have that kind of picked apart, right, then I can swap these and say if x squared equal to y squared, then, or x squared is equal to y squared, then x equals y. Which is false, again, with the negatives. Pretty standard move. If you've got a square and you're not including the negative portion or maybe the positive portion, then you have to consider that, right? And so here it's false, because if you think about -2 squared is equal to 2 squared, right? -2 squared is equal to 2 squared. They both give you 4, but -2 is not equal to 2. 3.1, done. Any questions about those? So really take your time, and it takes practice, I'll say that much. Truth tables. These are fun. They're tedious, but they're fun. We start off nice and slow, construct the truth tables of all these. I'm going to skip these because I think they're pretty standard, but let's just talk about, we only talk about the or and the and. So for the or statement to be true, just one of those two has to be true, and then the final result is true. For the and statement, both of them have to be true in order for the overall to be true. So I'm going to skip these. How about, let's see here. Should I copy this into our notes because it's a lot? I'll copy this one in here so we can write about it. 3.2 exercise. We want to rewrite the following with as few extraneous parentheses as possible. And we had those rules, the hierarchy rules, which let us eliminate some parentheses. And so here we've just got a lot of them. And I'm going to write it out kind of as wide as I can, or so I can muster. Bracket and bracket R, bracket, 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 or bracket S. First thing I'm going to look out for is if I'm putting brackets around just one variable, I don't need to do that. Nice. So no, don't do that. So here, note, I'll say brackets around a single variable do not do anything. Right, so they can be removed. I'm gonna cheat and copy this. And I'll erase all the brackets that are around just single variables. Also, what I like to do, and I think just in programming, you get really good at matching up your brackets really quickly, right? And so what could I have done here? I'll undo all these, undo. If you work your way through these, where does this one end? It ends here. And that's where those colors came from. All right, just closing up all these brackets, matching them all up. And these single ones are the ones that we're removing. And maybe we'll do a reverse copy, paste. Copy, paste. Okay, now I'm ready to remove these brackets that are only around one thing, because I don't need them. Okay. Couple more brackets left here. I want to preserve the meaning, obviously. And so the negation on the outside tells me that I have to negate this entire thing inside, right? So I need those brackets. Now, I didn't go and distribute the negation, which you could do if you wanted to, right? But we need these for the negation, right? It has to be applied to P and R. But when I look at these first set of brackets here, they're just wrapping up one essentially, right? The negation of this block. And so I'm not doing anything in with these brackets. And so here, these are not needed. I'm explaining, I guess. It's just a feeling. No, it's not. Because I've got these guys wrapped up in the brackets, and I know the negation is attached to this set of brackets or S. And I don't need to say that this is its own thing. So I'm going to remove that, but always just confirm that you've preserved the meaning of it, right? And here I'll make a note that we could expand this note. We could expand the negation. But the reason that I'm hesitant to is because what would it do? It would put a negation on the P, and remember, it switches the and to an or, right? That's confusing. And then it would put a negation on the R, which is actually kind of more characters than what I have right now. So that's why I don't want to do that. Let's try it. The negation, when we bring it inside, let's see if I can snag. Can I snag that little blip where it summarizes the switch? Because that's confusing in the beginning. Once you get it, or once you've seen it, rather. Where is it? Was it in 3.1 maybe? Or maybe we haven't seen it yet. I think maybe we hadn't seen it yet at that point. But it would be not P, or notice the switch, not R. But then I would still need what? I would need brackets around this. Why? To emphasize that it's this chunk or S. So this thing together or S. And so, but this has more characters. Than not P and R or S. Slightly. but we always favor the ones with fewer characters, but they mean the same thing, and you can confirm it with a truth table. Wow, can. I know. I guess we could do that, but we've got bigger fish to fry. Okay. Let's snag the second one here. I'll go quite a bit faster this time. Bracket, bracket, P, bracket, or, bracket, Q, bracket, bracket, and, bracket, bracket, R, bracket, or, bracket, Q, bracket, bracket. Right away, I'm going to remove the ones that are just on individual variables, right? So these ones, or maybe I should copy. Make copy. If it's on just individual things, I can remove them. Anything else I can do? We're stuck, right? I need to show that it's P or Q is one thing, and I need to show that R or Q is one thing, and then I need to take the conjunction of the two, the and of the two. So we're done. Sometimes it's easy. Said one of the skills, because we're going to be using truth to, hey, there's a huge rainbow out. Aren't we so lucky? Looks close too. Anyone live in Glenmore? Is that Glenmore? Yeah. Everyone's like, I don't know. Can't see what you see, Emily. I know. It's glorious. Oh yeah, what were we doing? Truth tables, truth tables. So you need to be able to set up truth tables, which involves knowing how many different combinations I have, because that's how you set up all your possible combinations. Take them in half, take zeros, ones, right? And we'll see some bigger truth tables, but part of that is figuring out how many lines you need. So how many rows in the truth table of a proposition containing 4 variables P, Q, R, and S. So I have P, Q, R, and S. And just in general, it's always going to be 2 to the power of however many variables you have. Right? Because they all have 2 possible options, right? True, false, true, false, true, false. Right? And so we would need 16 rows. And to start that table out, you would start with 8 zeros and then 8 ones, right? And then the next one you would have 4 zeros, 4 ones, 4 zeros, 4 ones, right? You start chopping it in half until you're alternating 0, 1, 0, 1, 0, 1, 0, 1. Yeah.
Where would the 2 come?
It's just the number of possible outcomes, true or false, is 2.
Oh, okay.
Yeah. And maybe I'll add that here. True or false. Nice. If we have 45 lines on a sheet of paper, you want to reserve 1 line for each line in a truth table. How large could the cardinality of S be if you can write truth tables of propositions generated by S on the sheet of paper? So you're limited to 45 lines. Bummer, right? So we just found that if the cardinality is 4, right? If I have 4 variables, then we would need 16 rows. So I still have quite a bit of room. So let's take it up a notch. What if I let the cardinality be 5? So I have 5 variables. I would need 2 to the power of 5, which is 32 rows. Okay, still have room. Let's try another one. Still room for one more variable? I was talking to myself, I think. Is there? Then let's do 6. Next logical option. I would need 64 rows, which is too many. All right. I don't have any halfway points or anything like that because I have to list all the possible combinations. And of course, there are fancier mathy ways that you could get this, could arrive at this. But that's not what I meant for you to do. I just meant for you to try it like this. All right. So the maximum number of variables that we can handle if we have 45 rows is 5. And we'd have rows to spare. Okay. If we have these propositions that are generated by 3 variables, P, Q, and R, which are equivalent to one another. Now, this is why we have to spend all that time talking about what does it mean to be equivalent? What does it mean to be biconditional? What does it mean to be all these things, right? And now we can use it. So equivalence, I did pull it in from the textbook. Just recall that this is what equivalent means. Let S be a set of propositions and let R and S be propositions generated by S. Okay. Then R and S are equivalent if and only if the biconditional statement of R to S is a tautology. Whoa. The equivalence of R and S is denoted by this kind of thicker double arrow, this thicker biconditional arrow. So what do we have to do? In order for the biconditional statement to be true, right, the values on either side have to be the same, right? Either from a 0 to a 0 or a 1 to a 1. And did I write a little? Okay. And then if the biconditional statement going back and forth is a tautology, then they are equivalent. So we can find the truth table or the truth values of each proposition, which means we have to find the truth values of all these propositions. And then we're going to see which ones have the same final truth values. That's a good start, right? To see if they bounce back and forth between each other. And then if it's a tautology, then they're equivalent, right? Another way to think of it is if they have the same truth values, they're equivalent. They're equivalent statements. Okay. Start off nice and slow here. P and R or Q, what do I have to do? So I'm constantly dealing with P, Q, and R. So I have 3 variables. So all my truth tables are going to have how many? 8 options, yeah? 2 to the power of 3. So I start by listing them. Start with 4 zeros, followed by 4 ones. Then for the next variable, I break that in half, 0, 0, 1, 1, 0, 0, 1, 1. And then for the final one, 0, 1, 0, 1, 0, 1, 0, 1. Right? This part has to be the same for all of those statements that we're going to work through. Okay? And then I should have given myself more room here, but at first I was thinking I would put all of them into this one little grid, but that was ambitious. So then I had to switch things up. But anyways, whatever. starting with P and R. So how you're going to build up these truth tables is you're going to break it down into tiny, tiny sections and work your way up to the final statement. So here, the first thing that I'm going to do is P and R. So now I've got my finger on P and R, and as I move my way down, and means they both have to be true in order for the statement to be true, right? So P and R is false, 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 true, false, true. Okay. So now you kind of ignore these unless you need them. But now we're taking this column that we just made and looking at this column or Q. All right, so you gotta make sure that you're not jumping around, right? Keep your fingers on the page. And so P and R or Q. So or means that as long as there's one, it's true. Okay? 0, 0 makes a 0. 0, 0 makes a 0. 1, 0 makes a 1. 1, 0 makes a 1. 0, 0 makes a 1. 0, 1 makes a 1. 1, 0 makes a 1. And 1, 1 makes a 1. There. Now we have the truth table for P and R or Q. Okay. Now, the problem with truth tables is me reading the truth table to you is not very valuable, right? And so what I want to do is I want to just kind of scroll through. So I did the same thing, and you have or will too, right? For all of these, but you will. Yeah. Gonna get so much done this long weekend. Blink and you miss it. It's over. I already know it and I'm already sad about it. All the things I was gonna get done. No. So just make sure, go nice and slow when you're building these truth tables, right? And you've got the solutions here. But what I want to do is just go to the and. So I made this big grid, okay? And I've got P, Q, and R still. I don't really need them, but it's nice to have. And then I just referred to them by part number, A through H. Yeah. And then what I did was, if I scan A, and then I'm looking for something that looks like A. So I'm looking for 2 zeros in the beginning, not this one, not this one. This one looks good. Okay, I'm going to check it. Yes. All right. And then I just indicated to myself somehow that these two have the same truth values. Okay. So now I do the same thing for all the rest of them. I try to match them up. Oh, I guess I knew that there were no more in here. It's all right. And I found that because what we want to check is the biconditional statement is a tautology, right? And so if I'm looking at A and E, if they're the same, they're going to be a tautology. Why? 0. So if 0, then 0, that's true, right? Thinking about the one section of the conditional statement, but also if 0, then 0, that's also true. And so now both of them are true, which means the biconditional is true. That's only going to be the case if they're the same, right? And so same with the 1, right? The first part is true, second part is true, then the overall statement is true. If I go backwards, true to true is also true. Overall, that yields a true, and I get just a series of 1s because those two columns are the same. And from there, I identified these equivalent statements, right? But you're looking for columns that have the same truth values. and then they're equivalent.
Professor,
Oh yeah. Woo.
so I don't know the exact difference between the biconditional and the double arrow biconditional.
Oh yeah. So here, if this biconditional is a tautology, which is always going to be the case if they're all the same. But I mean, in theory, I could have checked this one, right? I would get, okay, if I look at A to B, which I know is not, they're not equivalent, I would get, okay, 0 to 0, 0 to 0, that's a 1. 0 to 1, that's 1, right? But then 1 to 0, that's a 0. So then overall it's a 0. So then I wouldn't have all ones in that biconditional part. So it's only if it's all ones, then they're equivalent, which is a special case of the biconditional. Does that?
Yeah, so that's the tautology. And then what about the double arrow? What does that
Oh yeah,
mean?
so the double arrow, here I'll scroll back up because I brought it in, but I don't think I read it. Or I did, but that's okay. R and S are equivalent if and only if the biconditional statement is a tautology. And then the equivalence is denoted. So if it's a tautology, then you can write it as equivalence.
Okay, so the single arrow means like an operation, and the
The
double arrow
single
means
is a special case of this biconditional.
okay, I understand. All right,
Nice. Nice.
thank you.
But they're also going to be equivalent if they have the same truth values. It's weird. In some rooms, it doesn't show my pen, and in this room, it shows my pen. It's weird. I don't know. All right. I like it better when it shows the pen because then it's not bringing up weird colors just out of the blue. Or pink in my case. Well, I've been using more green, I find, lately. Green's like mellow. Is an implication equivalent to its converse? Verify your answer using a truth table. So an implication is something like if P then Q. The converse would be if Q then P, right? We already saw that. We already worked with the converse. And so now we're going to see if they're equivalent by checking if the biconditional statement is a tautology, which actually might help clarify the previous question. So if we just have two statements or two variables P and Q, then I only need 4 lines, right? 0, 0, 1, 1, 0, 1, 0, 1. Someone should auto-tune that. 0, 1, 0, 1, 1, 0, 0, 0, 1. It's all fun. I'm going to break up this biconditional statement into 2 parts. I'm going to do, or I guess I'm going to look at the implication first. Doing both of those things. If P then Q. Going from 0 to 0, that's true. 0 to 1 is also true. The only time it's not true is if I'm going from 1 to 0, that's not true. And then 1 to 1 is 1. Fine. Now you just have to read it the other way for the next column, the converse, right? Q. So 0 to 0, that's a 1. 1 to 0, no, no, no. That's a 0, because you're reading them the other way. 0 to 1, that's a 1. 1 to 1, that's a 1, and that's a more. Now, the biconditional statement, right, of these two conditional statements is going to be, okay, if I'm bouncing between the same values, then I get a 1, right? So 1 to 1, that's a 1. 1 to 0, no, that's a 0. 0 to 1, no, that's a 0. 1 to 1, that's a 1. This is not all ones, so it's not a tautology, which means that this is the biconditional, right? But it's not a tautology, and so they're not equivalent, right? The equivalence was the special case where this biconditional statement gave you all ones. And I think that
the biconditional
maybe
between
helps.
0 and 0 is 1.
The conditional, yes.
The biconditional between 0 and 0.
I don't have a
No, we don't have it.
0
We
and
don't have it,
0,
but just in case that
but
can.
it would be true, yes.
Okay.
It would be a
all
1.
right.
Like if this here was a 0, this would be a 1.
Okay, perfect. Thank you.
Nice. Which I'll undo because that would be confusing. But yeah, absolutely. Okay. Write the following in symbolic notation and determine whether it's a tautology. Whoa. That's a lot of work, right? First thing you have to do is break up the sentence into different variables, right, that you can work with. So if I study, then I will learn, right? We can now probably feel pretty comfortable translating that into a logical statement. I will not learn, therefore I do not study. That makes no sense, but it's got a true or false value, so it's logical, I guess. So what I did was just kind of chop this whole thing up, right? So I recognize the if then, and so if I study, which I'm going to let be S, I will learn, I let it be L. Doesn't matter what letters you pick. Is P, Q, R, doesn't matter. I will not learn. The only sneaky part here is that that's an and, right? It's kind of a hidden and, right? If I study, then I will learn. The statement I will not learn is and, right? It's kind of, you join these things up, and I will not learn, therefore I do not study. So when I break it down, I really only have two variables that I'm working with, right? S and L. S and L. So if S, then L, and not L, then not S. Wow, what a mess, right? But when you break it down into these little components, it's not so bad. But you do need to keep track of your brackets, right? Just to highlight that, okay, this was one part of the statement, right? If I study, then I will learn, right? Period. Second part is, and I will not learn. And then all of the, then I do not. Right. So I translated it into a logical statement. That's difficult, right? And then what do I want to do? Write out the following in symbolic notation. Phew, we did it. And determine whether it is a tautology. Okay. What am I going to have to do? First, I need to list my variables, all possible outcomes. There's only 2, so there's 4 rows. We're good with that, I think. And then I need to pick this thing apart and build it back up. So if S then L, 0 to 0 is 1, 0 to 1 is 1, 1 to 0, no, no, no. 1 to 1 is 1. And no, no, no means 0. Breaking it up to not L before I join it with this and. If you can see the flip side of this, you don't have to make this not L, but I really need to write everything down so I can see it. Otherwise, I just get so messed up. So I just made a new column, not L, which I just switched the L column, right? And then I made a new column where I joined this first one that we made and the second one that we made. The and is only true if they're both true, which is only for the first one. Then I'm gonna need, so now I've tackled this part. I have the truth table for this part. So if that, then not S, I'm gonna jot down not S again, just because I need it. I want it. And then I can go back and forth between these two. And from 1 to 1 is 1. From 0 to 1 is 1. From 0 to 0 is 1. From 0 to 0 is 1. It is a tautology. And with that, you did it. Any questions?
In this
Oh, one
case,
question.
the
Yes.
tautology is resulting from a conditional, not from a biconditional.
Yeah, so a tautology is just a general term when we have all ones.
Okay, understood. Okay.
Yeah, nice. Other questions? Are you ready for your long weekend? Have fun. No, I'm not gonna see you. I'm leaving you for next Friday. I'll do a video. Hey guys, be sure to like and subscribe.
Bye-bye. Thank you.